All right, back to the two-disc problem. We're just working on part B now. And part B, remember, looking back, we established earlier today, this asks about part B. Here, let's look up here. Says, show that the kinetic energy of the system decreases in this interaction and calculate the ratio of the final to the initial rotational energy. All right, so now, looking at part B down here, we earlier established that K is equal to L squared, angular momentum squared divided by twice the moment of inertia. And if you want to look at it, that was all the way back at the beginning of the day. That was our warm-up problem right here. Okay? We established by substitution that the energy of a rotating object could be given by the angular momentum squared divided by twice the moment of inertia. All right, so now we'll go back to our problem that we're working on, and that's this one right here. All right, so remembering that, all we got to do now is say that the moment of inertia of the rotating system to begin with is just the moment of inertia of disk 1. All right, that's the bottom disk. All right, so then when they're rotating together, the moment of inertia is that associated with the two that are rotating. Okay, so that's an important part of understanding this problem when we're talking about the kinetic energy. Only this one is rotating initially, so that's the only part associated with kinetic energy, and here they're both rotating together after the fact. So that we're going to use that moment of inertia, the sum of their two inertias of the two disks together, to be the inertia of the moment of inertia of the system when we calculate the kinetic energy. All right, of course, angular momentum is conserved. All right, so if we take a look here, we know, starting all the way here on the left, we know what we're looking for is the ratio of the new kinetic energy to that of the old kinetic energy. All right, and here's our generalized expression filled in for the primes. Okay, so the angular momentum after the fact squared divided by the moment of inertia after the fact. That whole quotient divided by the initial angular momentum squared divided by twice the moment of inertia. Remember, just the one disk is going to be equal. That's going to be the same ratio, right? This is just this equals this, and this equals this. All right. So now, since we know right here that L prime is equal to L, I just substituted L for L prime right here. So this is L prime. The rest of this stuff all in here is the same. So now, see in blue here, we cancel out the L squareds, and then we just flip everything around, so we get 2I over 2I prime is equal to K prime over K. Cancel out the 2's, and we get I over I prime, and then I we said is I1, and I prime is equal to I1 plus I2. As you can see, this right here must be less than 1, so that means that the ratio of the kinetic energies is less than 1, okay? And then it says calculate, but obviously we can only come up with an expression for it, and that is right here, that the ratio of their kinetic energies is equal to the ratio of the first moment of inertia to that of the sum of the two moments of inertia together, the system at the end.